Dequeue in queue. Dequeue operation, this is the operation of removing an element from a queue. So let us say there are a lot of people who are standing in a queue. Who will be the first person who gets to go out of the queue? It will always be the first person. So in a queue data structure, whenever you want to dequeue, that is remove an element from the queue, you always remove from the beginning of the queue. So this is rule number 1. Now coming to the implementation, you have array implementation and linked list implementation. Let us see how do you dequeue in array implementation, and then we'll also see how do you do this dequeue operation in linked list implementation. Coming to array implementation, you have an array like this, and let us say there are 3-4 elements. This is the front, and let us say this is the rear. So a rear pointer we already discussed. We call it a pointer, but it is basically an index. It tells you the index of the place where next element can be inserted. So at this point, let us say this is 0, 1, 2, 3, 4. These are the indices. So rear is at 3, means this is already filled till 2, and you can add any new element at 3. And the front pointer, which will always be here. So this will tell you which is the beginning of the queue, that is the front point of the queue. From here you can do dequeue. So how do you do dequeue operation? First thing, rule number 1, always see whether the queue is already empty. If it is already empty, there is nothing you can do. You cannot remove anything. So check if it is empty. How do you do an empty check? There are 2 things to check. One is if your front is pointing to -1. It is 0 index is this. If it is pointing to -1, it can mean that it is an empty queue. So this actually depends on how you implemented the queue. Let us say you implemented such that if it is empty, you will have front at -1. Then this would tell you that it is empty. Other way could be that in some implementations, front is equal to rear would mean the queue is empty. So let us stick to this, saying that if it is empty, you will make front as -1. From this, you will know that the queue is empty. Or let us say if rear is equal to 0. This can also mean queue is empty, because what does your rear pointer mean? Your rear pointer means the next position which is free for insertion. So if 0 is rear, that means 0 is free for insertion, which means there are no elements in the queue. So this totally depends on your implementation. Let us consider that you are implementing such that rear always points to the next available position. Then rear is equal to 0 will tell you that the queue is already empty. If rear is 1, 2 or something, queue is not empty. So let us consider it is not empty. Then how do you dequeue? The first thing you have to do is you have to access the element that is at the front. So let us say the elements here are 51, 40, 32. These are the elements. So first thing, you want to take 51, access it and give the value out. Return this value. This is first thing. Next thing, how do you show that the first element is deleted? One way is to increment the front pointer. You make front is equal to front plus 1. So now front will point to index number 1. This would mean the starting point of the queue is 1 and 51 is already dequeued. This is one way. The other way is, instead of doing this, you can move all the elements one step towards left. That is, you will move 40 to this position, 32 to this position. What is the advantage of doing this? Otherwise, just think you have only 2 elements in the queue. Okay, you only have 2 elements, but you did dequeue and enqueue multiple times. What will happen? All your memory space will be used up even though you have only 2 elements. How will that happen? Let us say initially this is the position. Let us say you inserted 2 elements. You inserted 10 and 11. Now you dequeued 10. So you dequeued 10, you made front as this, your rear is this. Let us say then you inserted 10 again. So you inserted 10 here. Then you dequeued 11. When you dequeued 11, your rear is now this, front is this, and you again inserted 11. What happened? Your elements are moving towards right, and even though you have space for five different elements, once this, let us say again you dequeued 10 and you again added another element, let us say 40. The space is exhausted. You cannot add any more element in this queue even though you are having 3 extra spaces. So in order to tackle this, the option is whenever you dequeue, instead of simply moving the front pointer forward, always keep front pointer here at 0. Make sure that your front is always at index 0. But whenever you want to dequeue, move all the elements in the queue one step towards right. So let us say 10, 11 and 12 IO elements in the queue. If you dequeue 10, move 11 to this position, 12 to this position. So this is the space effective way of utilizing array. But what is the problem here? Let us see what is the problem. What is the time complexity? Time complexity should have been order of 1 because you are simply dequeuing an element and you are incrementing the front pointer. But considering that you are moving all the elements in the queue one step towards left during dequeue operation, you will have to move n elements in order to move dequeue a single element, which means your time complexity will be order of n. So this is where queue takes order of n time complexity. So when we want to enqueue with array implementation, it takes only order of 1. But if you want to dequeue with array implementation, it takes order of n time. Okay. So it is order of n time, order of 1 space. Okay. This is the operation. Let us see the same operation when done through linked list. Let us say it is not array and it is linked list. So in case of linked list, what do? Here we already learned about this, that you will have a node and each node will have a pointer to the next node. This is how you implement linked list. And you will have a front and a rear pointer. So your front pointer will point to your first element and your rear pointer will point to your last element. So this is how you keep track of the beginning of the end and the ending of queue. So again, you have to do the empty check. How do you do the empty check? If it is empty, your front pointer will be null, your rear pointer will also be null. If both front and rear pointers are null, that means your queue is empty. There is nothing in the queue. You can't dequeue. So let us say it is not empty. Front and rear are pointing to something. In this case, what do? First thing is you have to retrieve the value. So let us say the values are 90, 81 and 95. First thing, you retrieve the value at the front. So dequeue is always from the front only. There is no concept of dequeue at any other point in a queue. So you are retrieving 90. I took the value 90. The next thing is I can remove this value 90 from here. How do I remove? In order to remove, I'll move my front pointer one step towards right. So this is my front pointer now. And this is removed. This means 90 is now no more reachable in this queue. Front pointer is pointing to 81, rear is pointing to 95. So now I can free this value 90. So what is the importance of free? We already discussed that this will remove it from the memory. So you removed it from the queue by changing front pointer to the next element. And after that you remove it from the memory by using free operation. So this is how you do it in a queue, in a linked list implementation of queue. And what is the time complexity? Here the time complexity is only order of 1 and space is also order of 1. So compared to array implementation, linked list implementation has an advantage in dequeue operation that it takes only order of 1 time and there is no need to do any reordering of elements. So one more thing you have to be careful is that if it is the case that the queue is having only one element, let us say queue is having only one element, both front and rear are pointing to same element. In this case, yes, you can do front is equal to front pointing next because this is pointing to nothing, which means next is null. So front pointing next would mean front will become null. But your rear is still pointing to this. So if there is only one element, during dequeue, you have to modify both the front pointer as well as the rear pointer. Rear pointer should also be made null if there is only one element in the queue. So what are the three things you have to see? One is if it is totally empty, you can't do dequeue operation. Second thing is if there is only one element, you have to make both front and rear as null. If there are more than one elements, that is more than one element, in that case you can just do front equal to front pointing next. So that would mean front will move one step towards right. So this is about queue and array implementation. So keep this in mind that whenever you already know the maximum queue size and you want to make it memory efficient, you can use arrays. But do keep in mind that dequeue operation would take order of n time if you are rearranging the elements after dequeue. So this is a problem with arrays, and we'll see how you can deal with this problem by using circular queues. In the circular queue lecture, we'll see that with array implementation itself, you can do both enqueue as well as dequeue in order of one time using circular queues. So we'll learn it in circular queue lecture. And then about linked list, you have to know that whenever you require dynamic sizing and still want to do in order of one time and order of one space, you can use linked list implementation.